All right, here we go. This is the last section. We're going to look at questions number 41 through 50 for the 1D Kinematics multiple choice pretest. For this first one, it says the area under the curve, so let's go ahead and draw. Well, that's not very good, but anyway, we've got velocity and time. Let's draw a red line for our constant velocity. And if I find the area under the curve, so let's actually use purple here. So I find the area, notice that it's just a rectangle. And the rectangle, if let's say this is 2 meters per second and this is 3 seconds, we can find the area underneath. 3 times 2 would be 6, and then that would be a meter per second times a second. Notice the seconds go away, and I'm left with 6 meters. So it actually gives us displacement. You could also think about the equation v is equal to d over t. If I rearrange it and I want distance, that's just velocity times time. Let's go ahead and look at number 42. This one is probably the hardest one to do, and it's the hardest one to explain too. So I have a velocity of a car. It comes to a full stop. So let's go ahead and use an equation. Vf squared is equal to Vo squared plus 2 times acceleration times distance. We can say the velocity of the car after traveling a distance of d over 2 is what? So we're going to try to figure out what this final velocity is. Initially, we're going to say the velocity is 0, and that's if we just plug some numbers in here. So this would be 1 plus, this would be 2. Let's go ahead and make this negative 0.5. and then make this distance 1. So if we do that, we see that we get 1 plus half of 2 would be 1, and times 1 is 1, so that would give us the 0. Now let's change it. Let's make it so that we find this final velocity. So for number 42, what we're going to do is the velocity of the car after traveling this distance. So let's go ahead and plug some numbers in. Let's go ahead and say we want to find the final velocity squared. That's equal to, so we're going to original velocity here is going to be 1 again, plus 2 times negative 0.5. Those don't change, but we want 1/2 now. The 2 and the 2 here cross off. So I've got 1 minus 0.5. So Vf squared is equal to 0.5. So if I find out what that is, that would be the square root of 0.5. And so now you have to get out your handy dandy calculator, find the square root of 0.5, and you actually end up with 0.707. The problem wants us to figure out, and it really gives us some weird answers. It's either greater than, equal to, or smaller than VO over 2. Our VO, remember, was 1, so that would be 1 over 2. And we notice that our VF now, so VO here, is equal to 0.5. We notice that our VF is actually bigger than that. It's 0.707. So your VF is greater than your VO. And that is the answer to this one. So that's very, very, very strange. So VF is greater than VO over 2. Sorry. So this is actually VO divided by 2. Just a weird question, kind of a weird way of looking at it, but actually works out pretty well. For number 43, very similar question. A car is traveling with velocity v. It's decelerated by a constant acceleration magnitude a. It travels a distance d before coming to rest. If you double its initial velocity, the distance required to stop would do something. So with this next one, this is number 43, we need to do a little bit of math to kind of help us a little bit. We're going to say that Vf squared is equal to Vo squared plus 2 times acceleration times distance. Now we're not going to use any numbers per se. If it stops, this is 0. And it doesn't change whether we have an initial speed of 5 or 10. What will happen is the distance required to stop, if I am going faster, the distance required to stop has got to go up. And so let's just think about this term. Okay, so we're going to outline the VO squared and the D. These two terms actually stay pretty much the same. The acceleration won't change and the 2 will stay the same. So if I take this one and it's 1 squared would be 1. But if I put a new velocity in it, this is 2 squared, then this number has to become 4. So if I double this one, just because they're on the same side, this one also needs to double. Okay, and that's basically how you would work this. So this would quadruple. So if this doubles, then we need to quadruple the distance. So we went from 1 to 4 here, 1 to 2, and then you square it. So that means this goes from 1 to 4. A little bit confusing, but not something that you can't do. Number 44, same type of thing, but this time they want to know about time. And so we can use our old friend VF is equal to VO plus AT. It's decelerated by constant acceleration. It takes t to come to rest. If the initial velocity were doubled, the time required to stop, what would happen to it? So if I double this one, now I also have to double the time. So your answer for number 44 would be double, and that's letter A. For number 45, a stone is thrown straight up. When it reaches its highest point, there's several things that happen here. So we've got a rock, it's thrown up. At this point, your velocity is equal to 0. But your acceleration, remember, is equal to the value of gravity, which is negative 10 meters per second squared. So the answer for number 45 is its velocity is 0, and its acceleration is not 0, it's actually negative 10. For number 46, suppose the ball is thrown straight up, reaches a maximum height, and then falls back down that initial height. They want you to make a statement about the direction of the velocity and the acceleration as the ball is going up. So we just said it. We said as the ball goes up, the velocity is positive, and the acceleration, due to gravity, has got to be negative. So for numbers 46, the velocity points up, and its acceleration points down. So velocity is up, and because this is negative, it actually points down. So that's number 46. For number 47, 2 athletes jump straight up. John has twice the initial speed of Harry. Compared to Harry, John stays in the air. And for this one, we can do a little bit of math again. So we have VF is equal to VO, and then this is plus G times T. Because we are jumping up, our original velocity, and let's just put the number 5 in, is positive, plus negative 10, and then we're going to multiply that times time. At the very top, remember your final velocity is 0, so now we can move the 5 to the other side. That makes it negative 5 is equal to negative 10 times t, and our time then is equal to 1/2 of a second, which is, remember, no decimals, 0.5 seconds. For the other person, the final velocity, again, is 0. The original velocity is twice. So John has twice the initial velocity. So we're going to put 2 times 5 plus, and then this is still negative 10, and we want to find the time. 5 times 2 is 10. Going to move it to the other side. That makes it negative 10 is equal to negative 10 times t. And so this person is in the air for 1 second. So we actually can double the time if you double the original speed. So once again, if you double one thing, you have to double this one because the gravity stays the same and our final velocity is the same. For number 48, this one says 2 objects are dropped from a bridge at an interval of 1 second apart. During that time, both objects continue to fall. So let's do these 2 objects. Let's make a red ball and we will make a green ball. Let's say that we wait a second for this one to fall. So we're going to say this is what we see at 1 second. This one is also at 1 second. Well, notice we've got a distance. If we allow them to continue to drop, because this one is moving now at 10 meters per second, and this one's moving at 0 meters per second, when it falls, it goes down here and is now going 20 meters per second at 2 seconds. And you'll see that it's gone further. Why? Because its speed was bigger here than it was up here. So now we're going to fall a little bit further. For the green ball at 2 seconds, we are right here. And we're now going 10 meters per second. So you see that the distance here is much smaller than the distance here. So they will continually get further apart, so their separation increases. That's number 48. Let's go ahead and look at number 49. For number 49, from the edge of the top of a roof, you toss a green ball upwards with the initial velocity VO and a blue ball downwards with that same velocity. So we're going to take a green ball, we're going to toss it up, and oops, that's not green. Let's make it green. So we've got a green ball. We're going to toss that green ball up with an initial velocity, well, let's call it 10 meters per second. And we're also going to toss a blue ball down at 10 meters per second. So we're going to call it negative 10 meters per second, and it is going in this direction. So the green ball goes up. When it reaches, oops, let's change this to green. When it reaches the top of its path up here, its velocity is equal to 0. And then when it falls back down, when it gets to this point, it falls for the same amount of time. So if this time is equal to 1 second, its velocity would be 0 here. If it falls again for another second, you're right, the velocity here would be negative 10 meters per second. Because the original velocities at this point are the same, they both would hit the ground with exactly the same speed. And that's answer letter C. Yay, we're on the very last one. This is number 50. You drop a stone from a bridge to the river below. After the stones travel distance D, you drop another one. The distance between the two stones will always increase. And we proved that one when we looked at number 48, when we did the same thing. So 48 and 50 have basically the same answer, increase, and that is it. Hopefully those helped you.